Welcome to the mysteries of the cosmos. Time travel has fascinated humanity for centuries, inspiring countless works of fiction and scientific speculation. But what does science really say about the possibility of time travel? The answer is more complex than we might imagine. Einstein's theory of relativity opened the door to the theoretical possibility of time travel, challenging our understanding of the flow of time. According to relativity, time is not absolute but relative, and can expand or contract depending on speed and gravity. This time dilation is real and has been confirmed experimentally. Clocks on GPS satellites must be adjusted to compensate for these relativistic effects. A traveler moving at speeds close to the speed of light would experience time slower, allowing him to jump into the future upon returning to Earth. This journey into the future is theoretically possible and does not violate any known laws of physics, although practical limitations make it currently unfeasible. Traveling back in time, however, presents much greater challenges and could conflict with fundamental principles of physics. Time paradoxes, such as the famous grandfather paradox, pose logical problems that question the feasibility of time travel. Some theories propose that these paradoxes could be resolved through parallel universes or alternative timelines. Wormholes, hypothetical tunnels in spacetime, have been proposed as possible mechanisms for time travel. However, keeping a wormhole open would require exotic forms of matter with properties that defy our current understanding. The idea of closed time-like curves in general relativity suggests the theoretical possibility of time travel, but with serious physical limitations. Some physicists argue that Novikov's self-consistency principle could prevent paradoxes by ensuring that the past cannot be altered. Quantum mechanics adds another layer of complexity to the concept of time travel, suggesting possible solutions to some classical paradoxes. Quantum post-selection proposes that particles could travel backward in time, but only in a way that avoids creating paradoxes. Recent experiments have explored the behavior of entangled particles in time, offering fascinating insights into quantum causality. Although these experiments do not allow information to be sent back in time, they challenge our conventional understanding of the direction of time. The idea of late signals in quantum physics suggests that, in a sense, the future could influence the past at the subatomic level. However, these quantum effects do not translate directly into the possibility of macroscopic time travel as we imagine it in fiction. Stephen Hawking's chronological protection theorem proposes that the laws of physics might prohibit travel to the past to avoid paradoxes. This hypothesis suggests that the universe has intrinsic mechanisms to prevent the creation of time machines, preserving causality. Thermodynamics and the arrow of time present another obstacle: how to reconcile travel to the past with the inevitable increase in entropy. Thermodynamic irreversibility seems to be in direct conflict with the idea of being able to freely go back in time. Some cosmological models, such as Gödel's universe, theoretically allow time travel, but they do not seem to describe our actual universe. These models are valuable as theoretical exercises, but they do not offer a practical path to building time machines. The search for time travelers from the future has been unsuccessful so far, which some consider indirect evidence of its impossibility. However, absence of evidence is not evidence of absence, and the possibility of time travel remains a topic of active research. Particle accelerators like the LHC have been the subject of speculation about the creation of micro-black holes or time distortions. Although these experiments have not produced evidence of time travel, they continue to expand our understanding of spacetime. The idea of protected chronology suggests that any attempt to create a time machine would be thwarted by radiation feedback. This radiation would be amplified until it destroyed the time travel mechanism before it could work, preserving causality. The concept of cosmic censorship proposes that nature hides singularities where the laws of physics break down, possibly including time machines. This hypothesis, although unproven, could explain why we do not observe large-scale causality violations in the universe. Tipler loops, or infinitely long, rotating cylinders, could theoretically create closed time paths, allowing travel to the past. However, the construction of such objects is physically impossible, requiring infinite length and resistance to extreme gravitational forces. The possibility of sending information back in time via faster-than-light particles, such as hypothetical tachyons, remains purely theoretical. So far, no evidence has been found for the existence of tachyons, and their presence could violate fundamental principles of physics. The quantum grandpa killer experiment proposes resolving temporal paradoxes through quantum mechanics in parallel universes. This interpretation suggests that time travel might be possible without creating paradoxes, but at the cost of creating new timelines. The idea that time might be an emergent illusion, proposed by some theories of quantum gravity, questions the very nature of time travel. If time is not fundamental but emergent, the concept of time travel might need a complete redefinition. Causal loops in theoretical physics suggest situations where an event is its own cause, challenging our understanding of causality. Although theoretically possible in some solutions to Einstein's equations, these loops present significant philosophical and logical challenges. The search for a theory of everything that unifies quantum mechanics and general relativity could provide new insights into time travel. Until then, the possibility of time travel remains one of the most intriguing and challenging enigmas of modern physics. While travel to the future is theoretically possible, travel to the past remains a topic of intense scientific debate and speculation. The continued exploration of these concepts not only expands our knowledge of the universe, but also challenges our understanding of time itself. Thank you for joining us on this stellar journey. If you enjoyed this cosmic tour, don't forget to like the video. Subscribe to Mysteries of the Cosmos for more space adventures. See you in the next video.